Okay, so we're looking at section 2.6. Starting 2.6 and 2.7, talking about graphing. And 2.6 is specific. It's about some basic functions. These 5 topics are what we're going to be talking about. You really need to be reading in the book too, because we're going to cover 2.6 in one day today. So make sure you're reading in the textbook also. Let's look at this first thing about continuity. You don't have to write this down, but just look at it with me. It's saying a function is continuous, and this is a definition. It's continuous if you can draw the graph of the function without picking your pencil up. Now, that's a really informal definition. If you go further in math, it gets a lot more formal than that. But this is just an informal definition. So let's say I've got a function that looks like this. Okay, that's not a function. Let's see, it does like this. Continuous? Yeah, I drew it without picking my pencil up. How about this? No. I had to pick my pencil up to draw that function. Not continuous. So, as long as you're understanding that if you pick your pencil up, you're talking about a non-continuous function. That's all I want you to get out of that. If you end up taking calculus one of these days, you'll get into a lot more formal definition of what continuity is. But for us, this is good. Questions about that? All right, let's take a look at some examples. And again, you don't have to write this down. But look at A. Continuous or not? Yeah, I could draw it without lifting my pencil. But let's talk about the interval that it's continuous over. So the x's start way out there on the left at negative infinity, right? If I could go out there, this would be continuous over its whole domain. That function, the domain of that function is negative infinity to positive infinity. So I could draw that whole function without ever lifting my pencil off the page, if I had that much time, eternity, and that much paper. So we're talking about, this ties in the idea of domain and continuity. Look at B. What's the domain? From negative infinity to positive infinity. Is it continuous over that whole domain? It looks like it. So I'd say it's continuous over its whole domain. How about C? What's the domain? For the x's now. 0 and infinity. So it's continuous over that domain. Now you can't say it's continuous for negative x's because they're not even in the domain, right? All right, let's keep going. Look at D. Weird little function. What's its domain? Negative infinity to 0. Is it continuous that whole time? Yeah. E. Now, it looks like the domain is all real numbers except for 1. This is saying x cannot be 3. So we could say that one of two ways. We could say it's discontinuous at 3, or we could say it's continuous from negative infinity all the way up to 3, but not including, union 3, but not including, to positive infinity. So it's continuous over 2 chunks, but not over the whole domain. And the way you probably hear people say it is, it's just discontinuous at 3. How about F? Looks like it's discontinuous at 1, so I could do the same kind of thing here. It's continuous over these 2 chunks. So if you see a little open dot, that means it's not continuous there, because to draw it, I'd have to pick my pencil up. So there's some examples like you're going to see on the homework. Those all came out of the textbook. Question about that? All right, let's go on to the next little topic here in this section. Now then, we're going to look at 6 different functions. And these are called parent functions. You don't need to write this down, y'all. It's in the book. These are called parent functions because we can manipulate those parent functions, and we're going to do that in section 2.7. But for right now, what I want you to concentrate on is the name of the function, what its domain is, what its range is, where is it continuous, but here's the main thing I want you to concentrate on, this picture. Look at that picture I just circled. If you've got that, if I say, get a picture in your mind of the identity function, if you can recall that picture right there, then you've got all the other stuff. Because you can see from just the picture, just forget all the surrounding stuff. You can see from the picture that the domain is from negative infinity to positive infinity. You can see from the picture that it's continuous. You can see from the picture that the range goes from negative infinity to positive infinity. Now, why do they call it the identity function, though? Well, look at your table over there. Whatever x is, y is. So in other words, the y's are identical to the x's. So if I say, well, what's the y value for x equal to negative 1,000,000? You'd say negative 1,000,000 for the y. The little drawing on the right-hand side is just a calculator screen. But if on all of these you memorize the picture so that you can recall it or recognize it, then you're good on this. And we're going to need this for section 2.7, which starts manipulating these things a bit. All right, there's the identity function. Let's look at the squaring function. Just get the picture. It's a parabola. Just looking at the picture, could you tell me what the domain is? Is there anything x cannot be? Nope. So from negative infinity to positive infinity. Just looking at the picture, can you tell what the range is? What's the smallest it can be? 0. And it can go all the way up to infinity. From the picture, we see that the function is decreasing from negative infinity to 0 and increasing from 0 to positive infinity. That kind of thing. But if you got the picture in your head, you've got it. We know it's continuous. If I didn't already say that. All right, so there's a squaring function. Let's look at the cubing function. I'm going quickly through these because really you just have to memorize them. There's not much emotional talk we can do about the graph of a parabola. All right, here's the cubing function. Look at the picture. Continuous? Yeah. What's the domain? Anything. Negative infinity to positive infinity. What's the range? Anything. Now, what if on a test I put this drawing on there and said, what interval is it decreasing over? That's a trick question. Is it ever decreasing? No. Starting way out here at negative infinity, it's always getting bigger. Don't let this little arrow trick you. That function is all, the y values are always going up as we go from left to right. And if you look down there at the bottom, x cubed increases over the entire domain. That makes sense. Question so far? All of these have been continuous so far. Let's look at square root. Look at the picture. Just based on that, could you tell what the domain is? Just based on that, could you tell what the range is? Always increasing, and it's continuous over its domain. Well, if its domain is from 0 to infinity, it's continuous over that range of values. So there's a square root. This one's kind of weird. Here's a cube root. Can you recognize it? If you see it. If you can call it up in your mind and you see a picture of it in your head, you can go, okay, I know the domain is anything from negative infinity to positive infinity. I know the range is anything. Is this function ever decreasing? No, because as we move in this direction from left to right, the y's are always getting bigger. It is right there waiting for you. Thank you, ma'am. Like your shirt.
Thank you.
So there's I'm telling you, a bunch of homework problems on this section. They're just asking questions just like that. What's the domain? What's the range? Blah, blah, blah. Then we get to the absolute value. Now this one's strange because it's got straight lines. Just looking at the picture, is there anything that x cannot be? No. So we know its domain is all real numbers, negative infinity to positive infinity. The range, notice it can't get lower than 0. It cannot. So I know the range goes from 0 all the way up to infinity. Continuous? Yeah, I could draw that without lifting my pencil. even though it takes that sharp angle. This one decreases over part of its domain and increases over part of its domain. So which ones are we talking about here? We got 6 of them. The identity function, picture the graph. The squaring function, it's just a parabola. Cubing, square root, cube root, these are all different enough that you're not going to get them confused, I hope. And then absolute value. And what I want to do is look at absolute value in a slightly different way. So I'm going to break it down into 2 chunks, the left-hand side and the right-hand side. This left-hand side, over here, starting at negative infinity all the way to 0. What could I say about it? Is it increasing or decreasing? Decreasing. And notice something, that whatever x is, like if I just pick an x, like if x is negative 2, what's my y? Positive 2. If x is negative 1, y is 1. If x is negative 3, y is 3. So y is the opposite of what x is. So could I write it like this? For this left-hand side, from negative infinity to 0, f of x, that is my whole function over there, is just negative x. So if x is if x is negative 1 million, y is positive 1 million. Okay? Then we're going to look at the right-hand side, a different chunk. Starting there at 0, going to positive infinity, isn't the y value, f of x, just equal to whatever x is? Yeah. So if x is 3, y is 3. If x is 25, y is 25. If x is 1.7, y is 1.7. The reason I picked that is because that'll lead us into a discussion of these things called piecewise-defined functions. And this gave people fits last year in pre-cal. It gave people fits last year in college algebra and the year before that in college algebra. These are easy. These are easy. You just have to understand how to work them. Once you do that, it's like, oh man, I wish I had 15 of those on a test. They call these piecewise because they look like this. The function is written in 2 chunks, 2 or more. I'm adding 2 little doors. And here's the deal. We are coming into the function. Here's our input coming in this way. You're only going to get to pick 1 door. So if my input, if my x value is, say, 7, which door do I go through, top or bottom? How do you know? You look at this stuff right here. The if parts. Which door, top or bottom? 7. Bottom. Because 7, right there, would be bigger than or equal to 0. Okay, so what does that mean? That means I would do this part over here. In other words, my y value is just what x is. So if x is 7, y is 7. What if I send a 0 in? Which door? Bottom. And so I'm down here at the bottom part, and it says whatever x is, y is. So y would be 0. Confusing? What if I sent a negative 12 in? Top. So that says take your x, negative 12, multiply by negative 1, so 12. So you're always getting back a number from 0 on up. Can't be less than 0. That's really, literally as hard as it gets. Notice something, though. There's no overlap here. 0 is not included in both of those. The top one did not say less than or equal to 0, and the bottom would say greater than or equal to 0, because then, if I send a 0 in, which door would I pick? See, that function would not be well defined. Now, could I have said, put the less than up here and leave it off down there at the bottom? Sure, that would still work. So either way, just don't put the equal to on both of them. Let's look at a couple of examples here. Okay, I'll give you a minute to copy this one down. Okay, so a piecewise-defined function. This one has 2 pieces. Notice again there's no overlap. That negative 1 is not included in both those chunks. Just in the top one on this problem. So I'm going to send in a negative 5. I'm coming from this direction. Here comes my negative 5. Because part A says, find the value of the function when x is negative 5. Which door? Okay, top I'm seeing. So that says, if it comes in the top door, I'm going to take x and multiply it by 2. So this would be 2 times negative 5. That's my y. So in other words, if I go in that top door, that bottom part down there ceases to exist. It's like taking a fork in the road. I don't worry about what's on the other side. I'm just doing that top line up there. If I wrote it like this, if I said f of x equals 2x, there's nobody in here that would have trouble telling me what, if x is 5, y would be. And that's all we're doing. We're just taking one of those roads. All right, let's look at B. I'm sending a negative 1 in. Which door? Top again, because it says less than or equal to negative 1. So 2 times negative 1 All right, look at C. It says we're sending in a 0. Now I'm taking the bottom door because 0 is bigger than negative 1. So the bottom one says take your x, subtract 1 from it. That's my answer. And last but not least, I'm going to send a 3 in. 3 goes in the bottom door because x is bigger than negative 1 there. So this says take your x, subtract 1. You get that. I'm not trying to insult your intelligence. This is really as hard as it gets. Last example. All right, notice all this stuff on the right, all this stuff out here, is just deciding what door to go into. The actual function is this stuff on the left. And only one of those is going to be true at a time. So, again, let's send in negative 5. So I got negative 5 coming in. What door? Top. All right, so I'm going to do what it says to do. So I've got 2 plus negative 5, because that's what that top door leads to. So what, negative 3? So in other words, if x is negative 5, y is negative 3. Then send in a negative 1. What door? The middle, all right? So going in that door, it says just take the negative of whatever x is. Sending in 0. Again, the middle door, because 0 is in between negative 4 and 2. So what does it say to do? That. You only have to worry about one line at a time. 3. Well, 3 gets us down to the bottom door. And what I do there is say 3 times whatever my x was. 9. Y'all, that's it.